All right, today we're diving into something huge, a technology that could literally change everything, quantum computing. This isn't just theory anymore, so let's get right into the race for reality.
Just imagine a machine, a computer so powerful it could discover new, life-saving medicines, overnight, or maybe figure out how to create materials that could solve climate change. We're talking about problems that usually take decades, solved in a matter of hours. That is the incredible promise here.
Okay, but now, imagine that very same machine could crack every secret code in the world. We're talking about the encryption that protects your bank account, government secrets, literally everything. So yeah, that's the flip side, the peril. And believe me, it is just as real as the promise.
So, what are we really looking at here? Is this all just, science fiction? Or are we standing on the edge of the next big technological revolution? That's the big question, and we're going to dig into it right now.
All right, a new kind of computer. So to really get what's going on, you gotta understand why these machines are so just fundamentally different from the phone in your pocket. It all boils down to one huge change in how they think.
Okay, let's break it down with a simple analogy. Your laptop, your phone, they use bits. Think of a bit like a coin lying flat on a table. It's either heads or tails, 1 or 0. That's it. Simple. But a quantum bit, a qubit, that's like a coin that's still spinning in the air. It's not heads or tails. It's kind of both at the same time.
And that spinning coin state has a name. It's called superposition. This is basically the first superpower of a quantum computer. Because each qubit can be a 0 and a 1 at the same time, it means these machines can explore a ridiculous number of possibilities all at once. It's like having millions of computers working on a problem in parallel.
But wait, superposition is just part one of the magic trick. There's a second superpower, and this one is so weird, so bizarre, that it famously freaked out Albert Einstein himself. He called it spooky action at a distance.
What he was talking about is this thing called entanglement. Imagine you have two of those spinning coins and they're linked, mysteriously connected. If you stop one and it lands on heads, you instantly know, instantly, that the other one, even if it's on the other side of the galaxy, will be tails. That's entanglement. And the spooky connection is what lets quantum computers coordinate these incredibly complex calculations.
So, the quantum contenders. Okay, this stuff sounds like sci-fi, but who's actually building it? Who are the major players in this race to create a real working quantum computer? Let's meet the contenders.
So here's a quick look at the current state of play. The raw horsepower, if you will, is measured in qubits. And you can see the big names you'd expect, right? Google and IBM are right there at the top, pushing past the 100 qubit mark. But what's really interesting is that it's not just them. You've got players like the Indian startup QpiAI in the mix, which is super exciting to see. And things are moving fast. Look at just the last few years. You've got IBM unveiling its slick, modular quantum system 2. Then Google announces its Willow processor. QpiAI launches Indus, which is a huge deal for India's national quantum mission. And then you have Microsoft jumping into the hardware game with its very first chip. The whole field is heating up.
Okay, hype versus reality. Because with all these big headlines, you get a ton of hype. So we have to ask, how much of this is a slick press release and how much is actual proven science? Let's get real for a minute.
Microsoft's announcement is a perfect case study here. It got a lot of press, a lot of excitement. The headlines talked about creating a quantum processing unit and proving these exotic particles exist. But when other physicists dug into the science, they pointed out, hey, wait a minute. The data showed they could read a result, which is important, but not necessarily that the chip was doing a full-on quantum computation. Even the paper in Nature said, well, the data could also be explained by this other, more common thing called Andreev modes. It really shows just how hard it is to prove you've actually made a breakthrough.
And all of this really brings us to where we are right now, which is what experts call the NISQ era. It's a key term to know. It stands for Noisy Intermediate Scale Quantum. Intermediate scale is pretty simple. It just means we don't have enough qubits yet. But noisy, well, that points to the single biggest challenge they're all facing.
So, what are these major hurdles? Well, for starters, qubits are incredibly fragile. They're like the divas of the computing world. The tiniest vibration, a tiny change in temperature, and poof, their quantum state is gone. That's the noise. It's why you see these machines that look like crazy golden chandeliers. They're giant refrigerators cooling the chips to just a fraction above absolute zero. And even then, this fragility means they make a lot of mistakes, sometimes as high as one error every 1,000 operations. And the scaling problem, it's huge. To build a machine that's actually useful and can correct its own errors, we're going to need something like 1 million stable qubits. And right now, the best we have is around 100. So yeah, long way to go.
Promise and peril. So, you might be thinking, if the challenges are that massive, why are governments and big tech pouring billions and billions of dollars into this? The answer is simple. Because if they pull it off, the payoff isn't just big, it's world-changing. I mean, look at the immense promise here. A real quantum computer could simulate molecules perfectly. Think about what that means. Designing new drugs, new materials, new batteries from the atom up. It could solve these insane optimization problems, completely revolutionizing things like financial markets or global shipping logistics. And it could give artificial intelligence a massive boost, letting it process datasets in ways that are just impossible for us right now. We're talking about an impact on basically every industry you can think of.
But with all that incredible promise comes that peril we mentioned, a threat so massive, so destabilizing that it has its own ominous name.
They call it Q-Day. This is the hypothetical day that somewhere builds a quantum computer powerful enough to break basically all of the encryption we use today. See, way back in 1994, a mathematician named Peter Shor created an algorithm. And this algorithm proved that a quantum computer could solve the exact mathematical problem that all of our modern digital security is built on. And it could do it with terrifying speed. That's what Q-Day is all about.
And look, this isn't just some far-off sci-fi fantasy. This threat is taken so seriously that governments are already scrambling. This is a direct quote from a White House national security memo, and it says quantum computing poses significant risks to the economic and national security of the United States. It's why the race to build a quantum computer is happening right alongside another, equally urgent race, the race to invent new forms of encryption that are quantum-proof.
So, the future is quantum. Where does all this leave us? Well, the race is definitely on. The stakes are unbelievably high, and you just can't deny the pace of progress.
Just look at this roadmap for a second. The theory, the idea that this could break encryption, has been sitting there since 1994. Then flash forward to 2019, and you have Google claiming quantum supremacy with their Sycamore chip, basically doing one specific task that no classical computer could. Fast forward again to 2024, and they're showing real progress on error correction, which is one of those huge hurdles we talked about. And now, you've got IBM out there with a public goal of a billion operations system by 2033. You can just see it. The milestones are getting closer and closer.
So it feels like the question really isn't if we're going to build a useful quantum computer anymore, it's when. And that leaves all of us with the biggest question of all. When this revolution finally gets here, is it going to be the thing that saves our world or the thing that breaks it?